All right, this quick video should finish up our chapter 36. But anyway, 36.6, we're looking at magnetic forces and how they affect moving charged particles. So if I take an electron, I shoot it, and it's flying around, and it crosses a magnetic field. What is going to happen is, as long as it's moving perpendicular to that magnetic field, the electron will be deflected. Now, how it's deflected depends on, how is the magnet set up? Is it set up north-south? Is it set up south-north? There's some other things like that that we need to take into account. But the idea is, as long as it crosses perpendicularly, it will be deflected. If it is moving parallel to the magnetic field line, then it's not deflected at all. And if it's somewhere in between parallel and perpendicular, it's deflected some, but maximum deflection comes when it crosses perpendicularly. So here in this picture, again, this is in your book, check it out. What you'll notice is that we have this green beam of electrons that's flying through here. It passes through the magnet and it gets deflected up. So the basic idea is that the magnetic field is flowing from the north end of the magnet to the south end of the magnet. The electron beam is coming in perpendicularly to that. Well, there's a third direction of the deflection. The force is actually created in the Z plane. So we've got a three-dimensional action going on here. The magnetic field and the beam's direction might be your XY, and then your force that's generated would actually be a Z direction. You could say likewise that, Z and Y, and then the force is in the X direction. But the point is that we've got three dimensions to worry about here. And so anyway, force is going to be greatest when the particle moves perpendicularly to those magnetic field lines. At other angles, there's going to be less force, but the force becomes zero when the particle moves parallel to that magnetic field. And so the direction of the force is always going to be perpendicular to both the magnetic field and the velocity of the charged particle. So this is a deal, again, where what we're talking about is this is the Z direction if the other two are the X and the Y. And so the deflecting force is different from other forces, like the force of gravity between masses or the electrostatic force between charges, or even the force between magnetic poles. And that's because this force is acting in a completely different third direction, that Z direction, if the magnetic field and electron velocity are in the X and Y directions. Now, this is important. It helps to protect the Earth from particles that come to us from outer space and the sun. But basically, the Earth is surrounded by a big magnetic field. And so when these particles come in from space or from the sun, a large portion of them get deflected by that magnetic field. And so they never make it to Earth. And that's a good thing, because if they were making it to Earth, we would see a much higher incidence of cancer happening to humans on the Earth. This is also something that, a lot of scientists look at, in that for the last 500 years that we've been taking magnetic field data, we've noticed a gradual decline in the magnetic field around the Earth. And so we know every couple million years or so, the Earth changes its magnetic field direction. And so they don't know whether this change in magnetic field direction leaves us with nothing in terms of a magnetic field for a while, or if it is in kind of an instantaneous switch. If, it's something where we don't have a magnetic field for 500 years or 1,000 years, it could be a problem to the human race. A lot of people are going to die because of these particles that would come in. But if it flips over in a year, we're going to see some increases in cancer, but it's not going to be something that may threaten our species. So anyway, we do get this help from the Earth's magnetic field, so don't take it for granted. But what happens when a charged particle moves in a magnetic field? As long as it's moving perpendicularly or at some angle that is not parallel to the magnetic field, it will be deflected to some extent. Now, since a charged particle moving through a magnetic field experiences a deflecting force, if we take a current of charged particles and move them through a magnetic field, the wire will also experience a deflecting force. And so what we see is something along this line. If I take the current and pass it through a wire, and then put that wire initially here where this dashed black line is, what happens is that the wire actually gets forced upward. And then if we switch the direction of the current, it's actually forced downward. And so this can be a problem when we have some storms and things like that come to the Earth. It can actually put a stress on our electrical current carrying wires and things like that, because it can put this force on them, which could ultimately put too much stress on them that it could cause them to break. But this is kind of one of those occurrences, happens once in a while with the sun, with some big storms that it creates. But it's fairly rare, but does cause problems from time to time. But if the direction of the current in the wire gets reversed, deflecting force is the opposite direction. Force is maximum again when current and magnetic field are perpendicular. And if the direction of force along neither the magnetic field lines nor the direction of the current, again, this is that XY. Again, the current is going this way, the X, the north-south, the direction is the Y, then the force or direction that the current or the wire gets pushed is in the Z direction. But if the force is perpendicular to both the field lines and currents, it's going to be a force that's in that Z direction. So just as a current carrying wire will deflect a magnetic compass, a magnet will deflect a current carrying wire. So both cases show different effects of the same phenomenon. And this discovery that a magnet exerts a force on a current carrying wire created a whole lot of excitement, because once Michael Faraday saw this, he saw that it could be used to push things around, make an electric motor or electric meter. And so he discovers this, and it becomes a very important discovery and led to electric motors and meters, which are now a huge part of our lives. So what law of physics tells you that if a current carrying wire produces a force on a magnet must produce a force on a current carrying wire? Dun, dun, dun. That's Newton's third law. Again, equal but opposite forces acting on two objects that are forcing one another. So how is current affected by a magnetic field? Again, it is forced to be bent in that wire by the magnetic field. And again, the force is in a third direction compared to the direction the current is going and the direction the magnetic field is going. So this again led us to meters and motors, but basically, the way we're going to look at this is we're first going to look at something called a galvanometer. And a galvanometer is just a very basic way we can use some current carrying wire and a magnet to show how much electricity or current is flowing through it. We can measure it. And then if we work on that principle, but just make a little tweak in it and allow it to not go just half the way, but rather we allow it to spin 360 degrees, we create what is known as an electric motor. And so basically the electric motor just allows the current to make a change every half revolution that allows it to spin 360 degrees. So this is a galvanometer. Basically, these orange coils represent some current carrying wire that's been created, made into a coil. Inside of that is like a compass needle. This compass needle has been magnetized. And basically, when a larger current passes through this device, this wire, it causes more of a tweak or more of a turn in this little needle device. And so the more current that passes through turns it more. And so we could, create a little scale to show us how much current is passing through if we calibrate it somehow. And this is a fairly sensitive instrument. We call it a galvanometer. But galvanometers, more typically today, that was a very basic way that someone like Michael Faraday could have looked at it. But today, basically, there's a better way to do it, a more efficient way to do it. And it is to take your coil and mount it for movement. And we hold the magnet stationary. We can have a bigger magnet that way. And that coil then turns against a spring. That spring pushes a little scale. And again, the greater the current in the loops, the greater the deflection. And we would see a bigger number appear on our device. And so this is what a more current galvanometer would look like. Basically, you've got a coil of wire in here. It's attached to this device. Again, it would begin to turn once electricity was passed through it, and that would cause this arrow to change its direction. And again, we could number 1, 2, 3, 4, 5, 6, 7, or something like that, and we would be able then to measure how much current was passing through our wire. Well, a multimeter basically does the same thing. It has all of these components found inside of it. We just attach these red and black wires to a current carrying wire that would allow us then to see how much on this little device here, how much either current or voltage was passing in our system. And so galvanometer, if it's calibrated to measure current, we call it an ammeter. And if we calibrate it to measure electric potential, we call it a voltmeter. So if you look at this, probably one of these scales here, there's a black scale on the bottom and a red scale above on the top. One of them, the black, is the volts, and the other one, the red, is the current, or vice versa. And so an electric motor is just a slight variation that's created on a galvanometer. With the galvanometer, again, we stopped it from going more than 180 degree turn. And so basically with the electric motor, the current is allowed to change direction every time the coil makes a half revolution. And since it's allowed to change, that allows it to overshoot and spin to make a complete circle. And so the coil then is forced to the other half of the revolution. It continues in a cyclic fashion, and in doing so, we get this continuous rotation. But basically, this would be something like a magnet here. This would be our current carrying wire attached to our loop. Well, our loop then has this ability to spin inside here, because basically what's happening is this is not connected to the leads here, but rather brushes over the edges or outside of this contact. And in spinning around it and just brushing it, once it gets to a certain place, it is allowed to continue the spin. And then this could be attached to this loop here, could be attached to an axle or something like that might run a little electric car. And so again, these brushes are the things that typically wear out in an electric motor. They are relatively easy to replace, relatively cheap to replace if you're good at taking stuff apart. You can get into the motor, replace the brushes, and then get back out. The talent comes in, can you put it back together? And so as long as you pay close attention to how you took it apart, it's relatively easy to put it back together. But if you're like me and you're not really paying attention, you're just cranking your wrench and your screwdriver and all that stuff, you don't really pay attention to where stuff comes from, putting it back together can be a little bit tough. These days, how do you fix something? Google it. You can go on there and figure out how to do it fairly easy that way. But again, rotation would be continuous and drive some kind of axle or whatever your motor needs to power, and this would allow the loop to be continuous and the movement to be continuous, as long as those brushes made slight contact with the leads, and as long as current is being supplied from the battery to the motor. Now, larger motors can be made by replacing a permanent magnet with an electromagnet. And so this electromagnet does have to be energized by some power source. Your Tesla automobile, runs on these electric motors. And so you just need a big, battery that is going to power up this electromagnet. And so once you're able to do that, you can get some pretty good horsepower out of those automobiles. But many loops of wire round about an iron cylinder we call an armature. These armatures rotate when they are generated by the electric current. So the armature just makes it a more efficient, higher power coming out of your motor. So how is a galvanometer similar to a simple electric motor, and how do they fundamentally differ? Again, all it is a magnet and a current carrying wire. Okay. Basically, how do they differ? Again, the galvanometer is only allowed to rotate half a turn, whereas the electric motor is allowed to continue on and make one full turn. So I'll let you take a look at that real quick. You can always pause it if you need to. But what is the main difference between a galvanometer and an electric motor? Again, one more time, galvanometer and an electric motor both have a current carrying wire and a magnet. The big difference, again, comes from the fact that galvanometers only allowed to go halfway. Electric motor is allowed to spin all the way because it has a set of brushes that allow for 360 degrees of rotation. So that ends chapter 36 notes. very shortly here, I will get out a 37 notes. It's only 3 quick sections, and we're done with notes for the year.